perhaps it's interesting to tell something more about the circuit that I published a few days ago, and it was the A-Stabile multivibrator circuit. But the good thing and the special thing about it was that it was emitter coupled, and I've talked already a lot about that circuit in an earlier video. For instance, that the change in the voltage, the supply voltage, does not have a big effect on the frequency. Bend over somewhat at first. By the way, this is new. Here I want to tell more about it. Now it is 27 November 2023. The first circuit was earlier. Anyway, in fact the whole circuit is exactly the same. Only two tiny, adaptations were made. I wanted to make the frequency variable, so I needed a potentiometer here. That's the most important thing in this video. This potentiometer, with this potentiometer you can set the whole circuit to a variable frequency. Square wave frequency. On the higher frequencies it's no longer a square wave, it's more or less a sine wave. That will be the next video, when I have made this circuit complete. As a function generator, more ideas are, for instance, to change the square wave into other waveforms. For a sine wave that is not very difficult. You need a filter, an RC filter, but of course such a filter must be made to specifically made to certain frequencies. Thus, that means that for say 50 Hertz, when you want to change a square wave into a sine wave or on 50 Hertz, the filter must be made in a certain way and will completely differ from a filter where you want to change a square wave to a sine wave on 20 kilohertz or say 50 kilohertz or 1 megahertz. The resistor and capacitor values have to be changed substantially in that case. Anyway, the schematic again, only this demo here, it's a vlog. Here is the schematic, and I found out that this resistor is responsible for the frequency change. So that's the reason why I made this circuit here. Now you can change the frequencies of all the capacitors CX, and that is this capacitor. So when you switch in here different capacitor values, I will tell more about it, and you say turn that potentiometer here, a 470 ohm potentiometer, you can surely see that the frequency changes, and here are, say, my test results. I hope it's visible from this distance. I cannot move it too much because otherwise it could be a mess, but let me pan over very quickly. It's the emitter-coupled multivibrator. It's now 27 November 2023. 23. So when that capacitor is 220 microfarad, this is the frequency range. And when it is 150 microfarad, this is the frequency range, 22 up to 40 Hertz. And that is, say, that are the complete practical capacitors that I've used. And I've used electrolytics, and I also found out that with electrolytics, compared to non-polar capacitors, the frequency could change. But anyway, 220 microfarad, 150 microfarad, 100 microfarad, 57 microfarad, and of course I had to find a situation where the frequency bands overlapped. That's always very important. When you make a function generator, sine wave oscillator, completely the same idea and issue. And here are the other capacitor values related to a certain frequency band. You can surely make this circuit. Don't be afraid that it doesn't work. It will surely work. And anyway, it is a circuit from Fairchild of the 1960s. So in those days, these simple circuits had to work, otherwise there was a lot of criticism. Pen over somewhat again. So at the moment the highest frequency is 5.3 kilocycles, but I've done already say kind of premature tests, and I could surely get to 5 megahertz, 6 megahertz, and that will be, say, the second video. Let's see what happens. Put on the scope now the voltage. The supply voltage of this circuit is at the moment 29 volts. And like I told in an earlier video, there's not so much deviation in the frequency band when the voltage changes somewhat anyway. Now there's here this experimental capacitor. Let's see what it can bring. Again, I switch out the lights, and perhaps this is not very interesting for the pure radio amateurs because it doesn't go so high, because we are now on 9.7 kilohertz, but anyway the whole circuit works also on a radio frequency, say above 2 megahertz. Here's the tuning potentiometer. I've indicated in the schematic. I turn it now, let's see what happens. So this is the lowest frequency, 5.7 kilohertz, and here it is the highest frequency, 9.6 kilohertz. But of course, again, this is a kind of in-between demonstration of this circuit, and it doesn't mean that it is not useful for higher frequencies anyway. When you know a little bit of electronics, you will surely understand that. Here again, the waveform is a beautiful square wave. On 9.65 kilohertz, And when you make that capacitor, the frequency, the capacitor that is for the most part responsible for the frequency out, when you make it smaller, you will surely go to very high frequencies. So, thanks for watching, by the way. Beautiful waveform. Again, the schematic. And especially the most important adaptation is that you can make the frequency variable here. With the help of this potentiometer circuit, you can use it as a function generator. It sends out square waves, but of course with filters you can change that anyway. Well, pan over somewhat. Perhaps again interesting to tell, all these capacitors were, say, searched out to get to the certain frequency bands, and the frequency bands are here. Let me pan over somewhat. The red markings. So you can also use this circuit for a specific frequency that you want or need. Could be a low frequency, could be an audio frequency, could be a radio frequency, say above 2 megahertz, etc. Thanks for watching. Pan over somewhat. And here is that potentiometer that sets the frequency. Perhaps again interesting to show. And then I will stop.